we've been studying matter for like, a couple hundred years, right? Refined understanding of chemicals, and all of a sudden we discover that all that work we've been doing is on like this tiny fraction of what the universe is made out of. It's like you've been studying an elephant's tail for 200 years, and you discover it's only the tail. So look at what is the universe made out of, like a pie chart. 5% of it is stuff we know. 20% of it, dark matter. 75% of it, we have no idea. Dark matter is 5 times as heavy as all the matter we know about it. That's the familiar kind. Stars, planets, asteroids, etc. There's these huge, massive blobs of stuff out there. It's huge. It's everywhere. We just can't really interact with it very much. There's 4 major ways that things interact. There's gravity. If you have any mass at all, things get attracted. There's electromagnetism, which is, like 2 charges repel each other. And that's the major force that you actually feel. If I press down on this table, the reason the table doesn't get crushed or pushes back is that the molecules inside the table are holding tight on each other electrically. There's another force called the weak nuclear force. It's like electrostatic forces, but it's much, much weaker. And then there's a 4th force, which is called strong interactions. It's inside the nucleus. It's what binds the nucleus together. All of these things are just descriptive. We don't understand why any of these things happen. This is just like a summary of the things we've seen. It's like botany. Here's what we've observed. And so far, we can explain every experiment in terms of these 4 kinds of interactions. Dark matter has mass, but does not have electrostatic interactions, which is why we can't see it. It doesn't reflect light or give off light. For a while, people thought maybe dark matter was just a lot of neutrinos. But it'd have to be an enormous number of neutrinos, like a ridiculous number of neutrinos.
There's 2 classes of ways that we have evidence for it.
One way you see dark matter is things don't spin the way they should if there's only normal matter. There's obviously big clumps of normal matter.
There's another one that's really cool too. It's called strong lensing. Let's say you're looking out this way and you see a galaxy. If there is a big chunk of mass in the middle between you and that galaxy, then the galaxy's light can come around one way and sort of be bent into your eye, and it can also come around the other way and be bent into your eye. You can see a galaxy that you seem to see in 2 different directions, but the way it looks, its shape and colors and everything, are so similar that you're pretty sure it's not 2 independent galaxies. It's actually the same galaxy, just you're seeing it in 2 ways.
Gravity is the biggest way that we've seen dark matter because we know it feels it, right? That's why we call it matter. It's dark matter because we know it has stuff to it. It's like one of the only things we know about it. We've also seen sort of more direct evidence for dark matter, which is we saw 2 galaxies collide, actually the result of their collision. And we can see these galaxies each had normal matter and dark matter, and then they collided. The normal matter slammed into each other. The dark matter just went through itself. These enormous galactic-sized pieces of matter pass through each other.
And this is what's so cool about it, I think. It's basically this clash of worldviews. For a long time, particle physicists have been drilling down into smaller and smaller length scales. So, as you have the atom, then you drill down, you found the nucleus, and you drill down, you found quarks and stuff like that. And that's been going on in its own very successful way. And then, completely separate, you had people looking farther and farther out. So first you look and you see the solar system, then you go out and you see the galaxies, and you see extragalactic stuff. We're just one galaxy in the whole universe. And just kind of, in some sense, just recently, these 2 successful ways of doing science have sort of clashed. I mean, there used to be a joke that, cosmology, if you got anything accurate to a factor of 100, that was precision cosmology. People used to make fun of them because they couldn't measure anything, And little by little, particle physicists have had to start admitting that these guys are doing something important, really want to know what they find out. So now we have to pay attention to them, we have to go to their conferences, and little by little they're coming to our conferences too. So, there's this melding of cultures, basically. We're really exploring here, and we're in the early days. I feel like too many people feel like, yeah, physicists mostly have it figured out. They're like down studying the details of the details of the details. But we have no idea. We're only now, by looking at the details, realizing what the questions are we should be asking, right? So like,
Do you ever feel like when you were learning about the explorers back in elementary school, whatever, like, man, that would have been cool, but it's all used up, right? Like, there's no more continents to discover. It's not true. There's a huge amount of exploration to do. Here, we're about to illuminate a huge fraction of the universe nobody's ever looked at before. I mean, it's an amazing age of exploration. Simultaneously, we know that we know very little, which is important, so we know where to look. And we built this huge new tools. We have this collider. And the magic of a collider is you can make kinds of matter in a collider that you don't have around. It's this amazing quantum mechanical magic that's just turned on that's going to help us answer these questions. So these two things are coming together right now. I mean, people could look back in like 200 years at these years and think, well, this was the period that redefined our understanding of the universe. What you should take away from this is we don't know what the rest of the elephant looks like at all, and you should be ready for some surprises.